we have 3 fantastic talks coming up. And without further ado, I will hand over to Bob Carpenter for our first presentation.
Thanks. Okay, so I'm Bob. I'm going to be talking to you about our new sampler, Walnutpie. There's a whole bunch of people that I will cite as we go who are actually in the audience who are involved with this. And let me just start. So the view from 3,048 meters. We say the view from 10,000 feet in the States, but I figured I'd translate for this audience. So Walnuts is the new sampler that we've been working on for the last year. You can think of it as being like Nuts, but with automatic step size reduction to preserve the Hamiltonian. The same way Nuts expands the tree to make sure we get to a U-turn state, Walnuts is going to cut down the step size until we preserve the Hamiltonian. So what that's going to do is basically get rid of all the divergences you have in your models, right? If we need a smaller step size, you're going to get a smaller step size. We're going to combine that with Nutpie, which luckily Adrian already told everybody about. This is an amazing new system for mass matrix tuning that uses draws and scores instead of just the draws. It has a slightly different target that I'll talk about later. We're doing online adaptation, which is something that's new in Walnutpie. That is, I took Nutpie and figured out how to implement it one iteration at a time. So instead of doing adaptation in blocks, we're doing it one step at a time. There's also convergence monitoring, which means Walnutpie works completely automatically. It runs adaptation until it converges. It runs sampling until it converges. And I'll tell you how that works later as well. We've replaced the dual averaging inside of Nuts with Atom, which is much more robust and much faster for step size adaptation. We're building it all. We built it all in C++20. We actually released this now, like a couple weeks ago. It's built in C++20 on JThreads and concepts. There's a Python interface, and we were really inspired by Adrian's Nutpie implementation, where he built an implementation that would work for Stan models and PyMC models and all sorts of other stuff that you might be able to build in Python. So this is a sampler that's not being developed within the Stan project, mainly because I wanted complete control over this. And as soon as you bring something into the Stan project, all of a sudden 30 people get an opinion about what you're doing. I figured I'd build it and then throw it over the wall to them when we're done, because that'll be a lot easier from my perspective. And also, Stan isn't really about supporting all these other things either. So let's dive into the particular details. So I was originally going to try to do this with no formulas, and then I got nervous about that. So Gibbs self-tuning is something we've been working on for about the last year and a half. We call it GIST. HMC has 3 tuning parameters: a step size, a number of steps, and a mass matrix. HMC, if you think about how it works, it couples a new momentum term with a position term. Right? GIST is additionally going to couple in the tuning parameters, the step size, number of steps, and mass matrix, and it's going to be based on having a conditional distribution of the tuning parameters alpha given the position and momentum. Right? This is a free choice. You can make this P whatever you want and still get a valid sampler. Here's the first 2 GIST papers cited down below. Continuing what's going on is every iteration, what GIST does is it first Gibbs samples the tuning parameters based on the position and momentum. Then it resamples the momentum based on that, based on the mass matrix that you sampled in the first step. Sorry, it should be Gibbs sampling 1 and 2. So you're Gibbs sampling the tuning parameters, then you're Gibbs sampling the momentum, and then you're doing the standard metropolis within Gibbs step like happens in HMC. But now we get this extra Hastings-style correction term for having chosen a tuning parameters. We were really surprised that no one had really done this before. Right? This seems like such a simple idea, and we talked to a bunch of people, and they said, yeah, we kind of thought about something like this, but never really figured out how to make it work. So I basically now offhand, Milo and I locked ourselves in a room at Rutgers for a week and figured out how to do this. So the idea is you want to select this conditional distribution of the tuning parameters in such a way that those tuning parameters will be good for your local position, where you're at, theta and rho, and lead to high acceptance probabilities. And it turns out to be not that difficult to do that, which surprised us. We came up with this idea, and we were surprised that we could actually choose a P that actually worked here. So let's talk about Walnuts. Right? Walnuts was inspired by Gibbs self-tuning, but applying it at the leapfrog level, applying it at every leapfrog step. So the motivation here is multi-scale densities that have varying curvature in the posterior, things like Neal's funnel. Right? We want to allow, it works by taking macro leapfrog steps, where the idea is the macro leapfrog steps basically work just like nuts. which I'm not going to try to explain here. But the idea is each time we take a macro step, we start with the macro step size, and if that step size is too big to preserve the Hamiltonian, we cut it in half and try again. That means that's a deterministic procedure, so in reverse, that balance means we need to choose exactly the same step sizes going in the reverse direction. It turns out to be very, very reversible, right? You wouldn't necessarily think doing this through a whole bunch of leapfrog steps where there might be dozens of those or hundreds of them that this would actually reverse, but it reverses very well, right? Because it turns out it's very hard to go from A to B with a big step and not have to take the same size in both directions to preserve things. So macro steps, one or more micro steps. Detailed balance requires that matching in reverse that I put on the first slide. It's just a little more detailed when you're doing multiple steps like this. So this was in our third GIST paper, which came out in JMLR recently. This I need to actually see my computer for. I have an animation of this that now off did. Okay, let's hit play. Right, so what you're looking at here is nuts and walnuts on the left and the right. And what the thing in the middle is doing is telling you which step size walnuts is actually taking at any given point. Right, and you're seeing that the walnut sampler is able to go way deep into the funnel by cutting the step size down as it needs to and still gets preservation. Right, so the idea is that by doing this, we can go all the way down in the funnel and actually sample the funnel correctly with walnuts without turning it into a non-centered parameterization. Having said that, if you can make better parameterizations, walnuts will work better with better parameterizations too, right? But fair warning, the non-centered parameterization is not universally better. When you have a lot of data and or a strong prior, the centered parameterization is better. So let me pop back to the presentation here. Okay, so Nutpie. So what about Nutpie? Adrian already told us about it, but let me summarize what's going on. Nutpie, in practice, the bottom line here is it's a lot faster to adapt than what we did in Stan. In Stan, we just took the covariance of the draws to be the inverse mass matrix, right? What we're doing with Nutpie is we're actually choosing a different target. We're taking the geometric average of the inverse covariance of the scores and the covariance of the draws. Or sorry, the other way around. Right? I've actually got it written down here the right way. Right? So we're using the covariance of the draws for nuts. Right? Nutpie has a different initialization as well, which has been super helpful, which is an outer product of gradients. That's like you can think of an outer product of a gradient as a one sample Monte Carlo estimate of the Hessian, right? Because the expectation of the outer product of the gradients, the expectation of the negative Hessian are the same. They're both the Fisher information matrix, right? So the diagonal Nutpie has a much better. We're just looking at, I want to emphasize that in Walnutpie so far, we've only done the diagonal case. Adrian's gone a lot further inside of Nutpie with both low rank plus diagonal and normalizing flows, which we haven't gotten to yet. Right, so Nutpie is going to adapt in overlapping blocks using a geometric average of the draw covariance and the inverse covariance of the scores. That's the estimate of the inverse mass matrix. This stuff's all super confusing because, there's negative signs and inverses flying around all over the place, so I often get confused here. For those that don't know, the score is just the gradient of the log target density, right? The nice thing about this Nutpie target is it minimizes Fisher divergence. What is Fisher divergence? I'm not going to write the formula out, but I'm going to tell you. It's like KL divergence, but instead of looking at the difference of the log densities, it looks at the difference of the norm. It looks at the norm of the difference of the gradients. Right? So in other words, Fisher divergence is trying to match the gradients more than it's trying to match the densities, which I got a lot of insight from Adrian's talk yesterday as to why this is useful, because it smooths out the objective at the gradient level. Right? So Walnutpie uses an online form of Nutpie. What I mean by that is we're updating every iteration. We're not doing it in blocks. Nutpie did an interesting thing compared to Stan, where it took overlapping blocks, so it got more frequent updates. In Walnutpie, what we're doing is we're doing this online, but every iteration we do an exponential discounting of the past. And we set up that exponentially discounting schedule so it kind of mirrors the block growth structure of Stan. The way Stan adapts is it takes, by default, I think it takes 25 and then 50 and then 100 and then 200 draws in exponentially increasing blocks, right? What we're going to do is use exponentially discounting the past in such a way that it gives you a kind of continuous approximation of this block structure, right? The nice thing about this is it's going to converge to the asymptotic target, minimizing the Fisher divergence. Great, thanks. And the nice thing is this can be implemented in constant memory using Welford's algorithms. You might think this is super expensive, but the updates, at least in the diagonal case, are super cheap, right? So let's talk about convergence monitoring with automatic stopping. Well, we want to automatically stop. It's really painful in the workflow to say, oh, what do we want? Let's try 100 iterations and see if that works. Let's try 200. Let's try 400. One of the first things I built for Andrew Gelman when I started working with him was something that did iterative deepening and did that automatically, but nobody ever wanted to use that. This is much better. This actually monitors as you're going during warm-up and monitors during sampling whether you've converged. Right, we're running a bunch of parallel Markov chains. We're running them asynchronously. Each one runs in its own thread at its own pace. They're not synchronized in any way. What they're doing is each one of these chains is accumulating statistics. During warm-up, you're looking at the mass matrix that's getting estimated and the step size that's getting estimated. And during sampling, you're accumulating the mean and the variance of the unnormalized log density. Right? The stopping criteria for warm-up is going to be when the difference in the step size and the norm versus the average, the geometric average in this case, is below some threshold. So you set a threshold for R hat and say, stop sampling when all of these chains have gotten R hat below a particular number. Right? Why is R hat convergence monitoring enough? There's a really cool paper by Dudica Vats and I don't know Knutson's first name. The log density, the reason we chose log density to monitor is it's one quantity, so it's cheap to update, and it tends to be one of the slowest mixing parameters. There's no guarantee of that, but it's a transform of the core parameters that tends to be fairly slowly mixing. The nice thing is Vats and Knutson, for very strange motivation, they come from the Geyer school where you only run one chain, and they're like, how can we estimate our hat with one chain? Well, we can relate it to ESS. ESS we can estimate with one chain using autocorrelation, right? So this is what they came up with. Our hat turns out to be really not what we want to be using. This is why Charles, sitting up here, developed nested R hat, right? Because it turns out that R hat's going to be proportional to roughly the square root of 1 plus the number of chains divided by the cross-chain ESS, right? And that means that R hat is only going to converge to 1 when the ESS is big enough. Right? I can't have 100 parallel chains, each taking one independent sample. Our hat's going to be like, no, you got to keep going. You got to keep going until the effective sample size per chain is big enough. Right? The other thing that you can see about this formula is if we do split R hat, right, we're going to reduce our R hat. So just by construction, split R hat has a higher R hat value than if we didn't split. All right, so you could keep that in mind. We're not particularly worried about bias here. Like the thing that if you're a statistician, you're immediately saying, okay, we're doing some stopping criteria. What kind of bias is this criterion going to introduce? These things are so noisy that I don't think it's going to matter. Right? We haven't verified that, but I don't think this is something anybody needs to worry about. Nor did Aki think it was something. So I'm really confident when Aki said he didn't think it was something that we needed to worry about, because he knows a lot more about this than I do. Right? So what do we do with lock-free communication? Well, we're using lock-free monitors here, which is a cool construction using, this is something that Steve Bronder, who's over here, helped me with, and Brian helped with the code. I could not have built this without their help, at least not in a way that was this performant, because I hadn't coded a lot of C++ still since we built the first Stan. So communication is by these SPSC buffers that are lock-free, meaning we never have to lock. We never have to stop a thread with a mutex and say, wait till somebody else gets here. We don't have to wait till all the chains get to the same size. So we only keep the latest values from the chain. There may be a bit of update lag. Got it. And the monitor runs in its own thread, loops over the chains, reading their values, computes the convergence statistics, sets the JThread stop token to terminate. It will often do a few more iterations because inter-thread communication isn't as fast as we would like it to be because you want the threads to keep going very fast. So We're using Atom for step size adaptation. So nuts, Nutpie, and walnuts, they all use stochastic gradient descent, where the gradient descent is the objective is getting at the acceptance rate close to a target acceptance rate, and the error is implicitly squared error, which they never tell you, but if you if you kind of back out the error from the SGD algorithm you realize they're assuming squared errors, right? Which means we can just drop in Atom as a replacement for dual averaging, and probably, a good project for somebody to do would be drop in muon or one of the even newer sampling things and see if that's even better. So nuts and Nutpie use dual averaging, but we swap in Atom. So that's all I had to say. There's a GitHub. All the code's open source. It's on Flatiron Institute Walnutpie. We are about to submit the paper to archive as soon as Andrew adds some examples. And the people who are marked with an asterisk are actually here at StanCon. Thanks.
All right, fantastic. Thank you so much, Bob, for the fantastic presentation. Do we have any questions? Yes.
Thanks, Bob. That sounds so cool. So, of course, at some point, we would like to have it in Stan, and I hope we will get it through. So I'm wondering in this regard, since you also had to build kind of a lot of C++ stuff around it to make the interactions of the kind of different workers possible, I suppose, how difficult would it be to also do that in Stan?
I don't think it would be that difficult at all. Like, it's all open standard C++. I'm assuming C++ 20, which may be a little beyond where we can get with something like RStan, so that may be a problem until RStan catches, until R catches up. So that's always been kind of a thorn in our side, how slow R is to update their C++. It's the whole reason Stan was originally built in C++ 98 is because R hadn't gone to C++ 11, even though we were building it in like 2012.
Okay, makes sense. Thanks.
All right, any other questions? No? Okay, well, let's thank Bob again.